Also on my behalf, very welcome to all of you. First speaker today will be Gilles Frache from LIST, Luxembourg Institute of Science and Technology. And if you want to know something about AP MALDI, then LIST and Gilles Frache is really the person to talk to. And yeah, he'll show you some really nice developments that MASTEC together with LIST are developing on AP MALDI technology. Gilles?
Thank you, Peter. Well, as Peter said, I'm quite experienced with AP MALDI. I started to use with the AP MALDI source about 12 years ago. And since about 5 years, we have started to collaborate with MASTEC by establishing a European demo and application lab for potential European customers. And since 3 years now, we have started a development project, and I will show you some of our results for the very first time today. So quickly, the principle of this source and the main benefits is that it's compatible to a wide range of existing LC high-resolution mass spectrometers, mostly for all kinds of Orbitraps, let's say, from old generation LTQ Orbitrap Elites, Q Exactive, or the recent ones like the Explorers or the Trigrids. The design is very compact. Everything is integrated in this module. We can swap very quickly from electrospray to AP MALDI configuration. Typically within a minute, we can switch from LC to imaging mass spectrometry on one single instrument. We have several modes of operation. We can use the so-called pixel map to increase the sensitivity. We can also apply a small motion in each pixel. And if we want to increase the throughput of the imaging experiments, we can use the so-called constant speed raster. So it's a continuous mode where we can increase the throughput of the experiments. Focusing can be optimized down to, let's say, 5 micrometers. That's typically what we get on our system with the Explorers 480 that I have in my lab. The depth of focus is long enough to make the system quite tolerant to topography. And as we are working at atmospheric pressure, we can analyze biological samples in their more or less native form. Now the source is controlled with a very user-friendly control interface, and we have a conversion software provided with the source, and it allows us now to start sequences of images from any shape, not only rectangular images as we could only do in the past. Now with the new software, we can run sequences during several days in a row. And then to deal with the data, we can convert the data to AMZML5 format, and it opens the possibility to use a wide range of third-party software for data engine. Quickly, a few applications. Of course, we use it for biological tissue imaging. We can detect quite nice images for a wide range of lipids. Of course, thanks to the capabilities of the Orbitrap, we can identify the ions with a high mass accuracy. And using databases, we can identify a wide range of lipids. And as you can see, maybe it's a bit small, but the mass accuracy is very accurate. Of course, now with the new instrument, we can use internal calibrants, and typically the mass accuracy is very good and very stable all over the acquisition of images, because sometimes acquisition can last a few hours or even tenths of hours if needed, but the mass accuracy is really, really stable. We have a lot of activities around skin biology in my lab, and recently we have started to work on skin models, so in vitro reconstructed human epidermis, and of course this tissue are very small. You can see a cross-section on top. The whole thickness of all the layers of these model skins is about 100 and 120 micrometers. So if we want to describe properly the different layers of this model skin, we need to go down to very high lateral resolution. So we can go down to 5 micrometers. And this is, for example, a spectrum from one single pixel of 5 micrometers. So you see in the phospholipid mass range, we have plenty of lipids. Of course, we had to work a lot on the method development to have this very good result. So in our project on skin, we are now able to prove, for example, that active ingredients for cosmetic applications or for sunscreen development, we can prove that the active ingredient remain at the surface, which is mandatory for this partner. And then we can also see what happens in the skin and in each layer of the skin, using biomarkers or markers of inflammation, which can be expressed in the case of inflammation like a UV exposure. And we can also prove that the active ingredients which are developed for UV protection work really well, because we can see, for example, this hydroxycholesterol, which is a marker of inflammation, which is quite low in a control sample. After exposure to UV, we see that this marker increases a lot. And if the skin was treated before sunlight exposure, we see that the level of this marker is quite low. And for some molecules, so some identifications are not 100% validated yet, but we see some markers which are really located in a very small layer of cells. So we can really assess what happens in each layer of these models. Right, so I don't want to spend too much time on the applications, because I want to keep some time for the developments. So, of course, this source is very useful and very flexible, so the benefit of switching back to LCMS is really key for us. So of course, sample preparation is critical. That's why I wanted to mention here that really the spraying, the matrix spraying methodologies are very critical. But what we have seen, because we use the same analyzer for LCMS and for mass spec imaging, is that some lipids are detected and very interesting to monitor in skin inflammation, but we cannot see them in mass spec imaging. Being AP MALDI or vacuum MALDI system, some lipids are not good candidates for MALDI, even though we know that something happens to them by LCMS. So what we have developed over the last year is laser post-ionization. So here's the first compact plug-and-play swappable AP MALDI 2 system. So here we have the standard AP MALDI from Mastec on top. The only modification is just a small hole at the bottom of the AP MALDI source, and below this is the laser post-ionization system. So everything is attached together, so we can still remove this combination of two modules and switch back to LCMS. So we wanted to keep this design, to keep the possibility to work with LCMS on the same instruments. So the principle is that we have the standard laser, 355 nanometer, which will desorb ions, molecules, and we will intercept the plume of neutral using a second laser, which has a wavelength of 266 nanometer, and we have all the electronics which is integrated in the module, in the post-ionization module, to have a precise synchronization between the two laser shots. If we analyze a mixture of lipids, deuterated lipid mixture, Gilles Frache, we see that there is a significant improvement of the whole signal and also some lipids of interest. So it's a bit too wide, so let's zoom in. For example, yeah, there are some lipids like PCs which are good candidates for MALDI, so no worries, we can detect them without post-ionization, but with the post-ionization we see that there is an increase of signal. Triglycerides, which are not good candidates for MALDI, we see them now very well, and also PIs, which are not really detected in our conditions, and we see a significant improvement. Let's talk about numbers. We see here in this case increase of intensity by a factor of 10 to 76 in this case, so typically 1 to 2 orders of magnitude. So starting from conditions which are the optimum conditions for AP MALDI. Okay, so we didn't want to degrade the first results to exaggerate the enhancement. So we started really from conditions which are standard with the AP MALDI source to see what can be added with the second laser. So you see it works on the analysis of a lipid mixture on the target plate, but it works also for imaging. So of course, if we look at some lipids which are quite low in intensity, like PEs, we see on the left with the second laser, we see a significant improvement of the intensity in the image. But interestingly, of course, the lipids like PIs or triglycerides, which were not detected by AP MALDI imaging, are now detected thanks to the post-ionization module. So very interesting. Not only we increase the sensitivity of already detected lipid classes, but also we see new molecules. And we see new molecules because the laser wavelength of the second of the post-ionization module is different from the first one. So we have a different MALDI mechanism. So for example, if we take an example which is not a good candidate for MALDI polystyrene, well, proton attachment is really weak because proton affinity of polystyrene is not high enough. So with AP MALDI we still see some adducts, surprisingly. But using the laser, the post-ionization laser, you see a completely new distribution, which is coming from a different mechanism. Here it's resonance and multiphoton ionization. So we see radical cations of polystyrene, because of course polystyrene absorbs a lot at the wavelength of the second laser. So what we have seen, compared to what is published in the literature, this is a paper from the group of Ron Aaron, where he applied laser post-ionization to MALDI. In their paper, they see that there was a significant signal from protonated polystyrene. In our case, it's really purely photonic post-ionization in our case here. So the fact that we can have an additional mechanism of ionization opens very interesting possibilities to detect new molecules absorbing at this wavelength, and also increasing the sensitivity for some lipids to make them detectable at low concentration. So another example from the literature, in a MALDI-2 vacuum system, they detect galactosyl ceramide, which is a class of lipid which is of interest for us for the skin biology. And we see now, it's a brain section, but we see now with the post-ionization, we see this galactosyl ceramide with the post-ionization. So it opens perspective for the detection of this class of lipid, which is important for skin biology. Right. So to conclude, we have described today for the first time the first plug-and-play AP MALDI-2 module for Orbitraps. It shows an increase of detecting peaks by about 30%, according to our software. In metaspace, we have 3 times more annotations, because of course we can see more isotopes from isotopic patterns, so the annotations are better. This additional mechanism of ionization opens perspectives, for example, for the detection of drugs or molecules which have a significant absorption at 266 nanometer. It can be of benefits for polymers, for organic LEDs, for the detection of additives in polymers, for example. And very important for us, we wanted to keep this plug-and-play design. So this is the status of our research. So far, it's not yet ready to become a product, of course. It's really to give you a flavor of what we are investigating at the moment. There are still plenty of challenges for us, optimizing the alignment, the synchronization, to see what is the molecule-specific timings which are of interest for certain fields of application. We are also working on the ion transmission to be sure that we optimize the transfer of ions coming from different locations and different timing. And we also want to optimize the lateral resolution, because as we have increased the sensitivity, we can afford to decrease the spot size even more. With this, I want to thank you for your attention, and if you have any questions, happy to take them.
Any questions?
That's excellent work. So I have a question about the MALDI-2. What's the matrix you used?
Well, here we used sample preparation and all the conditions that we use in conventional MALDI. So we wanted only to see what is added to an existing experiment with validated parameters with the second laser. So it was CHCA matrix here in this case. Yeah.
So is there any difference among different matrices?
We did not investigate yet a wide range of matrices, but yes, there are some matrices which are well suited for 266 nanometer, like nicotinic acid or things like that.
Thank you.
Other questions? Everybody is blown out of the water. Let's thank Gilles again.